Huh? Same distance? Wait up there. All right, so let's take a look at stationary waves, right? All right, so today you want to take a look at stationary waves, right? If you remember what we did last week, what we did last week? Yeah, I have right, class. Right. So after camping was what? Yeah, we had class last week.
I was
Online, yeah. So last week we looked at all the wave properties, amplitude, frequency, phase difference, and all those other things, right? Right. So today we're going to look at something called stationary waves, right? All the time we've been looking at waves that carry energy. Right? Now we're going to look at a wave that doesn't carry energy, basically stores the energy. Right? So we're going to focus on a wave that we can represent looking like this. Right? This wave here is called a standing or a stationary wave. Right? All that will happen here is that the energy within this wave is locked between these points. This point here, these points here are points of no vibration called, anybody remember that? Nodes, very good. And these are points of maximum. This will be an antinode. This will be an antinode. Technically, this is an antinode as well. This is positive displacement, this is negative displacement. All right? So what we are trying to observe here are stationary waves that are made up of nodes and antinodes. These waves don't move. These waves just stand and they just vibrate right here. All right? So we're going to look at how these waves are produced, right? And we're going to learn how to calculate when these will happen. All right? These are basically superposition of a few other waves, right? Before I show you this simulation, we know it's a node, antinode, and so on. Right. How are these waves produced? So if I have a wall and incident on this wall is a wave, right? Let's assume that it regains all its energy after the bounce. Then what you will have is a wave going this way. When it hits here, the wave will rebound. And then when these two waves meet, what will happen? They'll undergo superposition, right? And the superimposed wave will look something like this. All right? So at the right frequency, these waves will superimpose and give it that big stationary wave. All right? We are going to learn about stationary waves now, right? So let's take a look at that simulation there. Let's take a look at this simulation. Oh wait, can I share it? Does it? That's what I need to share. Right, stationary wave. Right, not PhD. Physics class. Right, those who online, you should be able to see it in a little while, right? Right, I just have to come here and share. Yes, here we get lag online. Right, those who online, it might get a little lag. So if you want, you can go to the same website and take a look at it, right? All right, so watch this here. What you have there, you see that? What you have here, there's a red line, red dotted line, and actually it's not lagging that much on that. Right? You have a red line and you have the blue line. That's okay? When the red line and blue line superimpose on each other, they form in that green line. That's okay? That green line is a stationary wave. Take a look at it. See how it goes up and then come back down. See now? So that wave is not moving left or right. Right? It's just standing at one point and storing energy between it. Anyway, $1 All right, I'll look it up. So let's also adjust it. You're seeing the nodes. We have a node on it. We have a node here, and we have a node on it next side. Okay, so that's the first stationary way that you could possibly observe there, right? But I want you to pay attention and track. Right? I want you to pay attention and recognize that on both ends we have nodes. We have a node here and a node here. Right? I'm going to adjust the frequency now of the blue and the red. And let's see what will happen. All right, so that stationary wave is seen there. That is called your fundamental. That's your fundamental stationary wave, or sometimes called your first harmonic. All right. Let's change the frequency now and see if we can adjust it. Right. We get almost out of it. We can adjust it slower. All right, not perfect there, but watch it here. You know, see what happening there? That's the next stationary wave that we observe in there, but that change the frequency. It's not perfect because I have to get the exact frequency down here, but you will recognize that we still have a node and we have a node as well. Let's pretend that's a node, right? That's not really a node. But I have to adjust the frequency, but it kind of has it to it here. If I adjust the frequency further, you'll see now, if I adjust the frequency further, this is the third wave that we observe, for the third harmonic. But they all increase in by. But they all increase in by. Let me see if I can start. That it get back the first one. How do you reset it? Refresh it. What? On the top. What? So underneath here, it's on the top, you refresh. Yeah. Yeah. All right. So watch this here. This is called your first harmonic, right? This is your first harmonic, and this is when you have a node, an antinode, and a node. Okay? I am going to increase the frequency slightly. 0.067, right? Let's go up a little bit. Anyway, that's your first harmonic. If I go up a little bit, you'll recognize that it goes to second harmonic somewhere around here. That's almost it. Right? So from the first harmonic to the second harmonic, the wave increased by how much? How much it increased? Right. So the wave, the length of the wave. So initially it was like that. Now it's like this. This is by a half a wavelength. There's a half a wavelength, and there's a whole wavelength now. Look at it. Look at the third one now. Right? Look at the third one now. Jump down there. See that? That's the third harmonic, and it increased by how much? And then let's go up one more. See that? It's pi again. So every time I increase the frequency by a particular value, I am changing from first harmonic to second harmonic to third harmonic and so on. That's okay? So you could observe different stationary waves at different frequencies. That's okay? All those are stationary waves, right? And if you see the stationary wave drawn like this, it just simply means max to minimum displacement, oscillating right here. Okay? Right. Do I make it to these calculations? Yes. Yeah. No, I'll use the one from right here. Right. Watch this here. So this is the way the wave will look when you have a node on the beginning and the end. I am going to change it now. Let us, what do you reset it? This one here? Yeah. Let us, instead of starting with a node, start with an antinode. Watch out there. Let me pause it for you right here. Look at that first harmonic here. That's one. Look at that first harmonic here, right? You have an antinode on one end and an antinode right next to it. You recognize that? Right? So here was a node, an antinode, and then a node. Here's a node, antinode, a node, antinode, and node. If you look at the diagram there, it looks something like that. And it oscillates in between here. So here's an antinode and here's an antinode. You see that? So whenever your stationary wave starts with two nodes, start with a node and finish with a node, it looks like that. Whenever your stationary wave starts with an antinode and ends the antinode, it looks like this. Anybody could tell me how long a wave this is? How long of a wave? Half a wave. Right? Antinode to antinode is a half. Node to node is a half. Right? Anybody could guess if I were to increase the frequency, how much of a wave it would become? Yeah. It will be one wave. Let's see. Let me see. All right, so watch it here. I am going to increase the frequency slightly, and watch out it. That's the second harmonic. If I keep going up, you'll see a third harmonic, then your fourth harmonic, fifth harmonic, and so on. All right, I'm not sure if I could do it here. We can start with one and finish with the next one. Hold on, start with a node and finish with the antinode. That way. Now, frequencies adjust the size of the wave it gets in here. Anyway, you should have an idea there how it works now, right? Right, so this is a stationary wave. These are all the pointers on the stationary wave you need to know. This here, Azaria, is the stationary wave produced when you have two nodes, right? This is the stationary wave whenever you have a antinode opening here, you have an opening here and an opening here. All right? This is when both ends are open. So like you have a tube, right? So you have a tube and both ends open. The stationary wave in here will look like this, right? If both ends close and it produces a stationary wave in here, it will look like this. All right? But I have a little question, Shivish. That's not an accident. Right? Here I have a wall. Here I have a wall, right? I have a wall here and a wall here. What do you think will be produced here? Node or antinode? A node, very good. And here will be a node as well, right? So the first possible, always remember this, the first possible node to node is a what? Half a wave, right? So therefore, if I have two fixed ends, these are two fixed ends, the first harmonic will look like this. Okay with that? This is your first harmonic, right? Your first harmonic is your first stationary wave observed at frequency f0. Okay with that? And I just showed you if I had two open ends, right? Two open ends, it looks something like that. Antinode here, antinode here. Correct? What I want you to draw for me is the first harmonic with one node and one antinode. One node and one antinode. What does the first harmonic look like? Right, so we're trying to figure out what it will look like. Right, two fixed ends, two open ends, one open end, right? So one end open and one end is a wall. What will the first harmonic look like? So, okay, so what would it have in this end? Antinode, and what will have in this end? So, what is the first antinode to node? Quarter. You see that? So the first node to node is a half. The first antinode to antinode is a half. You see that? Yeah. And the first antinode to node is a quarter. So the wave will look like this. antinode node. That's okay? So this is your first harmonic for two fixed ends, two open ends, one end open. You okay with that? Yeah? And Alina, you remember what happened as we went from first harmonic to second harmonic? How much bigger did the wave get? It became a half a wave larger. Very good. Why it became a half a wave larger? What you say? Earlier, node to node is half a wave, right? Then when is the next node to node? Yeah, so here. When is the next node to node? 1.5 waves. So you would recognize it, or consistency increases by half a wave. Is enough, Chavish? So if we start at antinode to node, when is the next antinode to node? Here to here, half a wave later. See that? Here to here, quarter. If I add on a half wave, I reach in here. All right. So in short, from first to second to anyone, you're always increasing by half a wave. Okay, right? Right? So it's important you remember that. So let's do me one quick favor. Draw first harmonic, second harmonic, third harmonic for each one of these. Yeah, I did first here already. You have to draw second and third. Sometimes it's called fundamental. Huh? Please don't change the distance here. Everything will change, right? So draw your standing waves for first harmonic. I did it already. Do second for me and do third for me. Remember, when both ends open, you must always start with the anti and finish with the anti. When one end open, you start with the anti and you finish with a low. Right? If you're not seeing it, just remember, add on half a wave here. Add on half a wave here. That's okay? Always add on half a wave. Right? What I did for some people last time is I did a long stationary wave. So you would have seen at least so much. One, let's do 2 full cycles. Right? See that will help you figure out what. Right? We're not doing too bad. If you want to go to that thing, right? We do something like that. Take your time. If you're not seeing it, watch. Watch this all here. If you're not seeing it, right? Node to node easy, right? And I keep adding on a half. That easy, right? You okay with that? With the 2 nodes. But if it's anti-node to anti, yeah. Everything is add on half a wave. So wherever you have, add on half a wave. So yes, the 3/4 of a wave. But just make sure it looks, make sure when you draw it, it starts with an antinode. All right? Everybody have issues here? Right? These here, area. These two must always start with this one, even if you're adding on a half, it has to start and end with an antinode. This one here has to start with the antinode and end with a node all the time. Because the ends will not change. Right? What happens inside the wave will change a little. Here, all this one look like. Yeah, everything here is first harmonic. Right? So now you're adding on half a wave to figure out second harmonic for each one, third harmonic for each one. So if I add on half a wave here, I must start with a node, add on a half now. So it looks like that. This is the second harmonic with two fixed ends. What did third harmonic look like? 3. So that's 1, 2, 3. Right? That's the easy one. This is the hard one. Right? Because what you have to remember, Alina, is that you must always start here and finish with an antinode. So if I add on half again, how it will look? Start here, so I have to finish here. So it will look like this. See what I see now? But two ends open. It's from here to here, right? Antinode, antinode. So now, if it goes antinode to antinode again, I have to finish here. So your second harmonic is this. Okay? Here we have an half, it's the whole. But it starts with an antinode. So it's a whole wavelength. But it will look like this. It could be a full wavelength. But make sure it looks like this. Right? Right? So it has to start with an antinode. Right? Antinode. Antinode, node, antinode. Back up to. It has to line up with this, right? Right? You must have an antinode, antinode. You look like that? Yeah? Anybody confused? This hard, eh? So if you're confused, it's okay. Online, anybody confused? Nobody confused? So I guess somebody born on this one, sir. Oh, for really? Now it is. I will do it. You will look today, boy.
There's somebody that said today, that's why.
That's a bit.
No.
Pick up with a crash course, right? When you know in unit 1. Unit 1 is 6, 2.5. 2 per module. Or it could be like 1 6-hour class. Like 3 6 hours. I used to do that, but that's cool. For sure. Not so long. Right, and last one. Last one, we're starting at the antinode, antinode, antinode. I'm finishing quite here. So I had to fit that. That's 1, 2, and come back, right? I have to fit it in the same space, right? It's not big or small, I have to fit it in the same space. So antinode. right? All of them supposed to be the same length, huh? Always had to be the same length because we put in the same color, right? Again, you would recognize that they all increasing by a half, right? Everybody okay with us? Right, finish all these two here. Let's put some numbers here, right? Should be finish this. Now we're gonna do it. Now we're gonna do it. Right, we should do this one first. That should be. This one. Any questions online, Ranchu? Any questions? Neil, any questions? Alexia? Okay. So our next step is to predict when this will happen. All right. We need to predict when these will happen, and then we go back to the simulation and see if we can see if it will work. All right. Well, I can only get these two on that simulation. Right, Shivish, how will this look? To go from here to here, what I add on? Where is add on? From here to here. How much of a wave is add on? Right? So you're starting at an antinode. So you're starting at an antinode, right? And then adding on half. So it will look like this. See that, Arya? So you're here right now. So you have to add on a half. And that's a node. Then add on a half. And that's a node. Okay? Yeah. Yeah. Right? You don't know it first. Yes. It's based on where you're opening it. So you're starting here, Azaria. So you're here right now, right? Quarter of a way. Right? And you're adding on a half. Because you must always start here and finish at a node. So in your mind, you're trying to figure out where's the next node here. So you have to draw this. And then when you reach here, where is the next node? So you just draw that. So you start here and then finish it. Right? So you're starting here and then you're finishing that. All right, that's it. Any questions? So our objective now is to predict. Any questions online? Ishmael, you okay? Right? So which ones do you learn of? What do you learn of? Here's what you learn of. You learn of that the stationary wave between two fixed points must have a node and a node. Open, two opens, they must have a antinode and an antinode. One end open, antinode where the open is, node where the close is. And then add a half a wave. Right? That's all they're doing. Add a half a wave. Okay? Easy? Right, but here's the problem now. See how I was struggling on the simulation to figure out the frequency that this will happen at? Right, so now I don't want that to happen. Right, I don't want that to happen. So what I want to do now is to figure out F1. Right? How do I figure out F1? So watch this here. Let us say this entire length here is L. Right? So I'm using it for two fixed ends, right? It will work for anyone. Right, Nikolai? It will work for anyone, right? So for two fixed ends, it will work for any one of these examples. For two fixed ends at first harmonic, right? And as I said, some notes have first harmonic, some notes have fundamental, right? This is your first harmonic or your fundamental, all right? So at the first harmonic, right? That value L is how much of a wave? Half a wave, right? So L is equal. Yeah. Pi. No, that's not about length. That's phase, right? So the length of a wave is pi on 2. Okay, the length of that wave is lambda on 2. So lambda is equal to 2L. That's okay. So frequency is what? 2 pi. Frequency is what? All right. So speed of a wave is what? Speed of a wave is what? Frequency by lambda. So frequency is speed of the wave over lambda. That's okay? So frequency is equal, if I know the speed of the wave, the frequency is the speed of the wave divided by 2L. Right? This is the frequency that the first harmonic will happen at. You see that? They was listening to it. That's why I say maybe. Right? So watch here. Frequency is B on lambda. If we know B, which is the speed of the wave, right? The speed of the wave oscillating at. If we know the speed of the wave and we know L, we can find F0. That's not. L is the length. L is the length, which is L is the length of column. L is the length of the column. Right? Everybody okay with that? Let's see if we could find to mark favor. See if you all can find F1. F1 is here. Frequency here, what's happening? No, work it out. We'll try to remember it. See if we can do the same thing, Alina, and find F1. Just try it. See what you end up with. See if you can figure out what F1 is, the actual value into F1L. Sorry, VP and L. See if you can work out F1. Find F1 pass. Everything in the notes. Have a nice table in the notes. But I want you to work it out anyway. try to work it over. So L is how much? So this one, a whole wavelength lambda, right? 2 halves, yes, 2 halves. I was going to say. So lambda is, so the length of the column here is now one whole wave. Correct? So, well, lambda is equal to L. F1 is equal to V on L. F1 is equal to V on L. V on lambda, sorry, and lambda is this. Anybody recognize the relationship between two of them?
Yes.
F multiply this by 2. So F1 is 2F0. You see that? Earlier? So this is like, if I take it up, it'll be dark. I'm gonna say, no, it'll be recorded, it'll be darker. So that we have. All right, so F1 is 2F0. That's okay. And make a, if you're not a guess, F2 is what? 3F0. So now I don't have to play around with it. I can actually find F0 and multiply it by 2, multiply it by 3 to get these fundamentals here. You recognize that? And you can do it for any one of them. Are you okay with that? So the only time that you are going to observe those harmonics is at those frequencies. At no other point in time you will observe them. Online, I'll do it myself. What causes the wave to store energy? Right? So the reason the wave will store the energy is that the wave can't go anywhere. The wave kind of trapped between here. So all the wave can do is just oscillate right there. And because it oscillates in here, it's not losing energy anyway. So it's storing the energy within this space. Huh? Sound. For example, the sound the station. Not like. It will store energy between here. Oh no, on the fixed end, we don't have any energy. Now oscillate. On K and here, I mean? Yeah, no energy. Yes, I didn't take it off. All right, so watch this here. Right? What you're observing there is your first harmonic between two fixed ends. And the value is what? 0.067. So the second harmonic will happen when? The second harmonic will happen when, Shivish? Huh? .067 multiplied by 2. Which is how much? 0. All right, let's try it. 0.1. I think better to do that. You see that? Yeah. Right? Look at it there. That's the second harmonic. A little bit off. See that? A little bit off. It's slightly off. It's not on the 0 line. Everybody okay with that? And when will the third harmonic be?
Multiply the initial number by 3.
Multiply number by 3. Which one up? 0.198. 0.198. Yeah. 0.19.
I do it.
No, not this one. First frequency.
0.201.
Not again the door.
No.
That is the first value.
Right, I just multiply
By 3.
It's 0.20.
201.
Yeah. Oh, I didn't just calculate. I should have just calculated. I'm not.
A little bit over.
Oh, it's gonna take 20 minutes to do it.
How much you got? 0.201.
201.
Oh, 1.
Oh, say just about it.
I'll very mouse.
They kind of like right with it, and that's kind of edit it up. Oh.
Yeah. Yeah. Right? That's it. Are you that? That is your third harmonic. Are we as we do it? What's your but that is first value by 3. Right. My favor. Work it out like this. When tell me the frequency for the second harmonic here. 2 ends of what? Yeah, without answering. But the show is just 2. Outside of that stuff. Come on, work it out for me now, please. Just like how I work it out there, work it out, please. Work it out for this one. What is the frequency with the second harmonic up or not?
What would be the frequency of the second harmonic?
Right. Nalia, sit your hand up in the air there. See your point? So the second here will happen at Nikash. Yes. 0.201. Okay. So multiply by 3. Let's see. That's right. That looks like it. Does it look like it, or we skip a step?
I think it's skip one.
You skip one. Oh yeah. We skip F1.
Yeah, it is.
We end up at F2.
132.
1.1.
0.124.
134. Right. That looks like it there. So the answer is 0.134. That's okay? So you also multiply, right? Right? And you can work it out the same way and get it, right? Everybody okay with that? Everybody okay with that? Well, I can't get one open and one closed on this one, right? But that's the principle behind it. Huh? If it's up, let's go sine wave. Oh, where I can manipulate them. I know, I'm gonna clear all. All right, take a 2 minutes and then we start some questions. All right, online, take a 5 minutes and then we will take a look at some past paper. What? You have until 8 o'clock, yeah? Yeah, until 7:40. I don't like. Let's start back, right? So, Shivish, what do we have? Let's start. I'm not sure if you all see that question together. That's the only version I see. Soraya, what's here?
Oh, you're so delicate. I'm going to tell soon. I'm going to tell my dad.
Alright, so what's here? Right? That's the best I can do. I think picture is not the best, right? Right, so what's up there? Shivish, come before please. Right, I'm not sure what year it is, but let's take a look at it, right? Figure 2. Figure 2 shows a stationary wave, Soraya, on a wire under tension. Right? I don't know what it is. Right? And they gave it a frequency. So watch it there, the stationary wave, right? And they gave it a frequency happening at. If the length that's between here and here, if the entire length, right? If the length is 0.4 meters, calculate the speed of the wave. So they want you to calculate speed. What's the formula for speed again, Shivish? Speed of a wave. Frequency pi by lambda. So you have to figure out for that question what's the frequency and what is lambda. Okay, find the speed of the wave quickly there. Any answers online? What you got for wavelength? Should we go right first? That's how it is. So I want to do yeah. Right, so we know the access defined speed V is equal to F lambda. We know F, but we don't know lambda. All we know is that the length here is how much here. What's the length of the whole column? Up 0.4. And within that 0.4, how many waves you have? How much? How much? Oh, so it's 12 there. Right? So 0.4 is equal to 2 lambda. So lambda is 0.2 meters. And that's it. We're done. 1200 multiplied by 0.2. What's up? Up and lambda is
Set up on this 2 hours. Yeah. So you multiply the.
lambda is 12. No. So you have to ignore what I have here is for this wave. Look at that wave there. Column is how long? The column is 2 wavelengths long, eh? And how long is the column? 0.4. So it means that 2 waves is 0.4. So 1 wave will be 0.4. Right? This here was for this first harmonic. Okay? That's not what you observe in there. How much you got there? What's the answer? 240. Right? So that's wrong. It's 240 meters per second. That's our right, so it's 240 meters per second. All right. No, but answer why? The entire column there. What does that 0.4 represent? Right. Now we have the entire column from here to here. That is the length of the entire column. And how many waves you have within that column? 2 waves, right? So 2 waves is that whole column, which is 0.4. So you divide by 2. Next one. Next one. You see the next one? No. Hold on. All right, take a little read again. Let's take a look at this one here. An F column. An F column is formed using a glass tube, which is closed at one end. Right? So if one end closed, the next end what? Right? So one end closed, one end open. Its length may be varied, so we can vary the length of the column. Right? We can vary the length of the column from 0.5 to 1.8. Calculate the length at which it tuned in for up 280 would produce resonance. Right? Once you hear that resonance, all they want to know is stationary waves. When will stationary waves be formed? So you have to use the information there to figure out at what length they will observe stationary waves. So the first thing you have to do is what? One end open and one end closed, right? You have to figure out what the fundamental will look like. So which one will it look like? Which one? It will look like this, right? So now you know what it looks like. How much of a wave this is? Quarter of a wave. You have to figure out now what length you'll observe this at or this at or this at. Right? They give you the speed of the sound and they give you everything you need. You have to figure out what length you'll observe it at. So they are adjusting the lengths. So work out for this first. What length will this happen at? Think about it. Right? Right? And they give you speed, Alena, and they give you speed, and they give you frequency. So that means you can guess and find what? Lambda. And if you know lambda, you have to figure out how you're going to answer what they ask. Huh? Yeah. Start with length. Now you divide lengths. So when will the fundamental happen at Caleb? When will the fundamental happen at? How much of a wave? Correct. Right? What was the wavelength? Go ahead. So will the fundamental be observed? No, I just guided answer what you have.
Sorry. So what I had on my team.
Oh, great.
So we do 0 meters. So ready for some comes up. Just regular line. Second.
Right, so you have to adjust the lengths and see when you'll be able to observe one of these. You got found the wavelength already? And the wavelength would have been P on F, which is 340. 340 over 280. How much is that? 1.21. So will we observe it within this range here? Yes. We will observe the first harmonic. Can we observe more? Try to figure that out. No, you're not done? So will you observe the first harmonic? Yes. So you can write here, first harmonic observed. You have to figure out if anything else would be observed. And it's 4 marks, so you have a bit of working on it. Right. Oh, wait. We forgot something. That is the wavelength. That is not first harmonic. Nalia, when is first harmonic observed? When is first harmonic observed in this situation? A quarter of a wave. I made a mistake and draw. And that's a whole wave? 1.2 and the whole wave, right? No, you're not drawing anything. So all you have to do, first harmonic occurs at lambda and 4. Right? First harmonic occurs at lambda and 4. 1.21 and 4. How much is that?
0.6.
0.3. Exact? Right. My question, will the first harmonic be observed within this range? No. Go again. Calculate again. Find second harmonic. Alright, follow the action here. No. That was wrong. That's the wavelength. That was the wavelength. I made a mistake there. That was the wavelength. First harmonic is observed here when it's quarter of a wave. Right? Sure? How much of a wave is this? 3/4. So you had to find 3/4 of a wave. Uh, 0.3 by 3/4.
We already divided by 4.
1.2 by 3/4. Or we just
We
add
already
on.
divided by 4, so if we just multiply it by 3, we'll be able to find second.
Okay.
We divided by 4, right? So that's the quarter. Now, if we divide by 3/4,
But you got 0.9.
9.
So will you observe second harmonic
Yeah.
within the range?
Yeah.
Yes. Go again. Question asks me how many you'll be able to observe. When resonance occurs, when you'll hear the harmonics. So check out third harmonic, tell me what you get. Well, yeah, you could do that, or here what to do. And this is, 1.25 of lambda.
Yeah.
Right, just do that. So put 5 on 4 of lambda.
You get 1.512. So 513.
1 point.
513. Which would.
Will you observe it?
Yeah.
Go again, find fourth harmonic. Find fourth harmonic now.
So which would happen? Say you multiply 7. So
4 by lambda.
lambda, yeah. I got 2.1.
Will you observe that?
Second, that too.
So you need second and third, you will observe. Yeah. The question asks you calculate the length. Calculate the length when resonance occurs. Resonance occurs when you hear the stationary waves. Right? So you will not hear first harmonic, you'll hear second harmonic, and you'll hear third harmonic. Cannot hear fourth harmonic.
Multiplies 5. Yeah. So a delta attribute is a quarter. Now, if you multiply we want to have a true, so that's true. Like we did that's what actually when I was on 30, so I was like right there. Yeah. Look at the signs, I know.
Next one. One over 12. Where? No. Forget about it. I just plug it in a form. Try this next one here. You can see that? You see that? Come on, hurry up. Do this next one here. And we have the booklets here. Okay, one more. I know. I help you with this one. No help for this one. Calculate the speed of sound. The only help I'm giving you is that you should have an idea what the speed of sound is. Huh?
That's right next to one of my friends living since and he hasn't
Depends. If it's expensive.
yes.
Right, you done?
It is giant.
Depends to the thing and do this one at the same time. Because how much you got? Look it out fast. Right, Alina, what do we have here, Alina? They gave us frequency and it's held just above the top of the uniform Right, the tube connects inside the column of air above the water, whose level can be changed at the top below, right? At the top below, right? So you can adjust the arm thing. It's very similar to the last one, right? And as the water is drained, sound intensity of the fork is enhanced at 0.6. What is happening at 0.6? No, what is that? When they observe it? Huh? One of these we don't know if it's first, but we are observing a harmonic. Right? We are observing a harmonic, we don't know which one. And again at 1 meter. So at 0.6 is one harmonic, and then at 1 meter is a next harmonic. You have to figure out now how to find speed. So start from what you know. Speed is what? F lambda. You know what?
Yeah.
So you have to find lambda. You know what? You have to find lambda. Go ahead. Don't overthink it. Huh? It's simple. The only hint I want to give you is you don't know which harmonic it is. You don't know if it's first or second. Okay? No, you don't need to guess. And there's a reason why. You don't need to guess. Azaria, what are you doing next? Shirish. Delia, finish? Why? That's what? It didn't. Now when I share it with your buds.
Yeah, yeah. B is equal to F lambda.
Right, so the trick is to get lambda. How we getting lambda? How you find it?
That's the pressure.
And the speed of sound is how much? 300 and something, right? So you should get around 320, 330 around there. Huh? All right. So yeah, online you can message simultaneous now. Not going to do any simultaneous on it.
Yeah. These are like an answer. No, literally, when that form first without doing any question, I was literally thinking it was solving solving log is take the sum of math equation.
Anybody figure how to get lambda? Watch. It's on the board, right? It's on the board somewhere right here. It's on the board. It's somewhere right here. Any answers online? Huh? What do we know about, Nalia, about 0.6 and 1? There are two ones. Okay, there are two lines, right? What else you know? There are two harmonics, right? What do we know? We don't know if it's the first harmonic or we don't know. It can be 10th and 11th. It don't matter. It don't matter which harmonic it is. But what happens between harmonics? Right, the difference between two harmonics is always what? Half a wave. The difference between two harmonics is always half a wave. So what is the difference between those two harmonics? Right, gamma over 2, which is 0.4. So it don't matter which harmonics it is. And you divide and subtract. Right? So let's pretend that 0.6 is the 9th harmonic. And 1 meter is the 10th harmonic. Because the question said they are two consecutive ones, right? Then the difference between two harmonics is always what? Right? So whenever you subtract it, that will be equal to half a wave length. What? Think about it. Think about it. So, one.
Yeah, look at my street. Well, I thought that. I don't know Spanish. I just Korean. I think.
All right, so lambda on 2 is 0.4. So lambda is 0.8. So speed is 440 multiplied by 0.8, which is 350.
That was correct.
That's what you get. Right? 350. Huh? Why?
Honestly.
You know some process? Well, you can play first.
Actually, well, I mean, yeah, I it's
Well, watch it. Yes, for the second one. So,
Skateboard and deep on skateboard. I understand.
we're going to dispute that that's 0.6. All right, nice. One more and we done. Yeah.
I'll get the apple with the
Yeah, this one. Yeah, this one. All right, next one.
apple vision fruit. Ew.
Last one, all time, last one.
Yeah.
Last one, yes. Take a read. Huh? Yeah, you did.
What? Hey, I did this. No, I did a lot.
Last one, Olive. Hurry up. Hey, hurry up now. Sean, going for talking. What's it? Catching shit up of the video class.
I think it's enough actually. It has what you can. It's just we can consider this and this as one of one, two. Yeah.
Yeah. So they said it must have three antinodes, right? But will it be nodes on either end and nodes on either end? Or will it be? Why?
Because it have two words.
Well,
So what about the water?
Hopefully,
both ends are fixed. Right? Both ends are fixed. Look at where the pulley is. They have a weight there. So that end can vibrate.
Okay.
And the next one attached to a wall or something.
So equally is considered as a.
No, not the pulley, the weight. The weight acting on the end of it makes it a fixed edge, so it can oscillate it.
So this is
So how will it look?
like after.
It will look like F2 here on the board. Okay? Why Shivish? Why will it look like this one here? Shivish. Why Shivish? Show me the three antinodes here. Show me the three antinodes. Write an equation, still have one more part.
what's the easy part?
Write an equation to the wavelength. Oh, by the way, they gave you the length here. You saw that? They gave you the wavelength up there. Last question, I'm finished.
Like. These are opposites. So like it's like a
Should we try it out? All right, so for this one, the length is 2.76, right? Right, so 2.76 is how much? 2.76 is how much of a wave? Should be 1.5. How much is that? 1.5. Nice. 3 lambda 2, and then solve for lambda. What's that? That's it, right? Hmm? I can't remember. Oh, yeah. So they have to oh, sorry. They have to calculate lambda as well. So they want a general equation with n. Anybody get to figure it out? Okay. So length is equal to what? Very good. N lambda how much? 4, 2. It'll be 2.
Yeah.
When it's 3 antinodes, 3 on top, 2 underneath. Right? That's the formula there. All right, so when it's 3 antinodes, 1, 2, 3, and the length was equal to 3 lambda 2. Yeah? So if it's 4 antinodes, it'll be 4 lambda 2.
Yeah.
Right? All right, Claudia. So that is your stationary waves, right? Get to my favor and we read out the little notes in the handout, right? Same thing we did, right? We just read out the little notes, and we have a couple more things in this module, right? There was extended calculation, and the next things are moving on to the fraction interference.